All right. I now make it 6 o'clock UK time, 7 o'clock in Central European time, which is means I think we are ready to go. Hello everyone. Welcome to the first um, lecture in the European Mathematical Society, the EMS lecture series on the mathematics of education. Thank you for joining us on this Friday evening. We will be running 6 of these sessions over the next 6 months. We have one per month, sort of 4 or 5 weeks apart. Please do check the schedule, but they will always be at this time on Friday evenings. I will be your host throughout. I am Dr. Tom Crawford. I am a mathematician based in the UK. So I teach at the moment at the University of Oxford and the University of Cambridge, and also do lots of things online with my website and YouTube channel, Tom Rocks Maths. Now, before I introduce our speaker for today, this being the first lecture, I will give a quick overview of the purpose of the lecture series, especially with it being a brand new initiative from the European Mathematical Society. The idea of these webinars is to basically act as a resource for those working in the teaching profession, and as such, we will be hearing from leading experts to explore critical issues and innovative approaches in mathematics teaching, curriculum design, and policy making. As Anne Dooms, who is the chair of the Education Committee, as she explained it to me, with the current shortage of skilled maths teachers, we value those that are choosing this teaching profession and we want to support them better, which I think is a fantastic sort of, let's say, motto or motivation behind the series. This particular series will focus on the importance of foundations and hierarchy, how we learn and learn maths in particular, what content choices are mostly made in the math syllabus and why, how to help kids that struggle early on in their mathematics education. We then have a talk on common misconceptions when being introduced to algebra. And finally, we will look at the impact of AI on maths education. There will, throughout all of these webinars, be a chance to ask questions, and we would love you to do so. There is a specific, I think, 15 or 20 minutes at the end when I will be fielding those questions to our speakers, and of course today to Anna. So there is a Google form, and we do have a QR code that we will share with you somehow shortly, which will allow you to submit questions. So please do that so we can get to those at the end. And that's probably enough of me talking. So it gives me great pleasure to introduce then our first speaker today. This is Professor Anna Stokke, my apologies. Anna is based at the University of Winnipeg in Canada, where she conducts research in algebra and algebraic combinatorics. But she also is very passionate about mathematics education, which is, of course, what she will be talking about today. Anna's Chalk and Talk Maths Education podcast has topped the education podcast charts in the US, Canada, Australia, and New Zealand, amongst others. And she is the recipient of countless awards for teaching excellence, community service, and educational leadership. Her lecture today is titled Why Foundational Math Skills Matter and How to Improve Them. Anna, over to you.
Well, thank you for that lovely introduction. And I'm here in Winnipeg, Manitoba, where, as you can see, is very sunny and very cold, and it's 12 p.m. So I'm going to talk to you today about why foundational math skills matter. And I'm really honored to be giving the first lecture in what I'm sure will be a fantastic series on math education. And I'm especially grateful to Anne Dooms and Nuno Credo for the invitation. So I come to this topic as a mathematician. I'm not an education researcher, but I do know a lot about math education research at this point because I've been working in math education advocacy for over 15 years. And I've had to educate myself on education research during that time. So a bit about my background and how I came to be in this space. I became interested in math education when my own children were in primary school. And at that time, I became rather alarmed, I would say, and frustrated by the way math was being taught. And on the other side of things, I would see my own university students, and they would often struggle because they didn't seem to have prerequisite skills. And so that led me to advocacy work like math outreach. I founded an advocacy group at one point and public engagement in Canada. I also run a nonprofit after school math program for kids in grades 4, 5, and 6. And more recently, I started the Chalk and Talk podcast, as Tom mentioned, where I speak with researchers and practitioners about what evidence tells us about what works in math education. So I'm going to focus on foundational skills today, why so many students seem to be missing them, what I think is going wrong, what I think can be done about it, and what we can learn from other countries that seem to have turned things around. So I'll start by saying I think we have an international math problem. Math performance has declined in many countries, and we can see this on PISA and TIMSS results, particularly outside East Asia. So we see similar downward trends across North America, much of Europe, Australia, New Zealand. And it's not due to the pandemic. The pandemic definitely worsened things, but these trends kind of started before that. And in many countries, math scores have been slipping for a decade or more. So why should we care? So I'll give you a second to think about this, and then I'll say why I think we should care. So first of all, when students struggle with K to 12 math, they're much less likely to take or be in a position to take courses like algebra, calculus, statistics, or courses that use math. Like a lot of courses use math, a lot of fields use math, like physics, chemistry, etc. And that matters because math is foundational to a huge range of careers, often high-paying careers. The STEM fields, economics, finance, technology, engineering, health sciences, even data-intensive social sciences, and also the skilled trades. But there's another issue, and that's lost human capital and unrealized potential. And I am convinced that many more students could be successful in math, or they could go much further in math, but they never get that opportunity because the foundation is weak. And in addition, a lot of studies have found positive correlations between early math performance, later academic success, and future earnings. In fact, and many people might be surprised by this, but early math performance has been found to positively correlate more with later academic success than reading. So this brings me to the role of foundational skills and why I care about foundational skills. And it's because math is relentlessly hierarchical. Okay, so I'll give you a second to look at my lovely stair picture here. So math is really like this huge connected network of topics, right? And you can pick like a topic and you could trace it back through its prerequisite skills. You could really trace it back to elementary school. And you can't access higher level ideas without fluency in those earlier ones, right? It's like the steps on a ladder. And if steps on that ladder are missing, it becomes really difficult to access the later concepts. So, and you can't reason your way around missing prerequisites. And these gaps, like they compound over time, right? And so it just becomes worse and worse over time if students are missing those gaps. So for instance, if you're trying to do algebra and you can't do fraction arithmetic, algebra is going to be really hard. And algebra is really like the gateway to higher level math, right? And the fraction arithmetic, if you can't do that, maybe that's because you're having trouble with basic addition or multiplication, or maybe you don't know your times tables. So I think it's really important to keep in mind that math is relentlessly hierarchical, and not everybody gets that because I don't think all subjects are like that. But it's something in math that we always have to keep in mind that it's very cumulative, which makes it difficult for students if they lose steps along the way. And so I want to give a recent example that got a lot of news coverage. Okay, and this comes from the University of California, San Diego. So some of you may have seen or read this report. And so, okay, so I'll start by sort of explaining the situation, what happened, and then I'll kind of show you an example of the test that they gave students. Okay, so this comes from a formal report out of the University of California, San Diego. And the math department had began noticing a large increase in the number of students who were placing into remedial math. So when they're coming to university, they're taking a placement test and they're being placed into remedial math, a course called Math 2. And instructors in that course were seeing what looked like a problem with students who couldn't do, middle school math. They were having trouble with middle school math. And so in fall 2023, they gave those students a short diagnostic test that covered basic skills like arithmetic and fractions, rounding, simple algebra. Over 100 students wrote the test. And I'm going to show you some of the questions on that test and what the results looked like. And something to keep in mind is that, many of these students had completed pre-calculus or even calculus. And so if you look on the right-hand side, you should be able to see the percentage of students that were able to answer these questions correctly on this test. And now these are students that were placed into remedial math. And you look at this and it's rather alarming. And what's also alarming about it is UCSD is it's a really good university. It's a very selective university. And so you can see, students were even having trouble with 7 plus 2 is blank plus 6. Only 75% of students were able to answer that correctly. And when you get to the fraction arithmetic, it starts getting really bad. And of course, the basic sort of algebra and working with exponents, that sort of thing, these students had a lot of trouble with that. Now, I mean, we could talk about in the whole report, it's an excellent report. And they talk about why they think this is happening, why students were ending up in UCSD and not able to do this basic math. But I want to talk about a bigger issue because I think there's a broader issue here. That why are these students getting through high school at all, unable to do basic middle school math? And I mean, I don't think UCSD is an outlier. I think it's a widespread problem, at least in North America. And if we're waiting until university to address missing foundational skills like this that go back this far, we're waiting too long. This is a big issue. Students should be mastering these foundational skills in school before these gaps have a chance to accumulate because there are huge downstream effects to this. And so let's talk a bit about this. And I definitely recommend grabbing this report, reading it. It's an excellent report. And they give recommendations for how to deal with this issue. But I wanted to bring it up because I wanted to talk about the larger issue of students actually graduating from high school unable to do basic math. So here are some of the downstream effects. And so I'll let you look at that for a second. So once students are placed into remedial math, when they get to university, the downstream effects are significant. And one of the most immediate is really there are much higher DF and withdrawal rates for students placed into remedial math. And even if they do finish the remedial math, they tend not to do as well in later math courses. And this is well documented, not just at UCSD. The gaps in that remedial classes are trying to fill, they're just too large, right? And it requires a lot of practice to become fluent with all those missing skills on that ladder. You can't just decide that you don't want to fill the gaps or that we're not going to fill the gaps because then the students are not going to be able to succeed in those later classes. And there's also just a substantial loss of time and money for these students. Like they might spend extra semesters taking non-credit courses that delay progress toward their degrees. And so that means additional tuition, living costs, etc. And just check out this quote from that UCSD report that there are data that show that few, if any, students who place into Math 2, that's that remedial math course, have successfully completed an engineering degree. And so students then are unable to continue in the program they want to continue in because of the math. So I think, that this is reflecting a deeper structural problem in math education that we need to address. And this isn't even to mention the kids that actually don't get to university, right? Because they're missing out on math skills. And so, I think prevention is better than remediation. So I want to outline four key issues that I think are contributing to some of these problems in math education. Okay, so I'll let you look at that for a second. So I think, we have to look upstream and think about what is the core cause, like what is causing these problems to happen in the first place. So I think the first thing to think about is curriculum. So you want curriculum content, good content and well designed. I'm going to talk a bit more about each of these, except maybe not as much the testing. You want instruction that actually helps students to learn. You want your teachers to be well prepared. You want them to be in a position where they can teach math, that they know the math and that they know how to teach it well. And then you want testing. You want to make sure that students that they have mastered the skills that you want them to master. So let's start with curriculum. So what should a good math curriculum look like? So good math curriculum, it's a detailed plan for building knowledge over time. So it should specify what students need to know, and it should make that very clear. They shouldn't be, we don't want vague goals or broad competencies because then teachers don't know what they have to teach. Parents don't know what students are supposed to learn. And that content needs to be carefully sequenced because math, as we said, is hierarchical. The order in which ideas are introduced really matters. And third, a curriculum should prioritize mastery of critical content for later success. Not everything is equally important. In addition to that, some things in math take a lot longer to get good at than other things. They need more practice and time. Like some topics are prerequisites for almost everything that follows, like fraction arithmetic. And early math should really explicitly prepare students for algebra by ensuring that they have fluency with those basic skills like number operations and fractions. If in early grades they don't do that, students they'll hit a wall when they get to algebra. So when we see, large numbers of students struggling with basic skills in algebra, I think curriculum is one of the first places to look. And so I'm going to give, just an example of what I mean by vague curriculum outcomes versus very specific, clear curriculum outcomes. And actually, I actually took these examples from, the first one is from Scotland's Curriculum for Excellence, and then the other one is from England. So, so you can see the first one. I'll just give you a second to read it. Okay, so the first one says, I can share ideas with others to develop ways of estimating the answer to a calculation or problem. Okay, So that's very vague. The teacher probably wouldn't know exactly what they're supposed to teach there. It's really not clear. It's specified that the students need to be able to share those ideas with others, and we don't know what that means. The second one, pupils should be taught. You wouldn't think you have to say pupils should be taught, but you actually, it's not a bad idea. And we'll talk a bit more about that in a second. So pupils should be taught to round any number to the nearest 10, 100, or 1,000. So that's very clear. Like it's telling you specific actual math knowledge that we want students to have. You know what they're supposed to know, the teacher knows what they're supposed to teach, and we can assess if they've actually learned that thing. And then the other thing that sometimes happens, at least, and this is very common in Canada, for instance, is weak curricula. They might delay important outcomes. They may delay them, dilute them, or omit them entirely. So, for example, it's quite shocking, but in many Canadian provinces, students are not introduced to fraction arithmetic until grade 7 or 8. And so they don't get enough time with those skills. Okay, so in a hierarchical subject like math, postponing those prerequisites, it means less practice with the skill, and it will cause students to be unprepared for any skills that it relies on. So let's just say a little bit about teacher preparation in math. Okay, so I'll give you a second to read that, and then I'm going to talk about it. And I want to stress, like, this is not about teacher effort or teacher commitment. Teachers are very committed. They have a tough job, and it's an extremely important job. But this is a structural problem. It's about how we prepare teachers and the tools we give them to do their jobs well. Like, everybody deserves to have the tools to do their job well. So particularly in K to 8, and I don't know if this is true across all of Europe or not, right? I'm Canadian, and so my experience is sort of grounded in what I see here. But particularly K to 8 teachers in a lot of countries are often generalist, and what that means is they teach all subjects, and they may not have like a solid footing in math, and they math may make them nervous, that sort of thing. Okay. And then when you have vague curricula that don't specify exactly what you're supposed to teach, what skills are important, and you're not sure because maybe you haven't taken calculus, you don't know what skills are needed to do well in calculus, you don't know what topics to prioritize. You might find it also difficult to judge, when a student might have a misconception with something. And you can't teach what you don't know. And if you don't know what to prioritize, instruction will suffer. So then the other issue is that teacher preparation programs, they don't always prioritize pedagogical theories that lead to math success. And I'll say a bit more about this in a moment. But I want to say, like, I often refer to this kind of as like the perfect storm. Like if you have teachers that may not know the math, and then you have a very weak or vague curriculum, and then the teachers are being told to use methods to teach that don't really work that well, learning goes very badly. It's like a perfect storm. Okay, so let's talk a bit about, and I said something about this already, I just kind of alluded to pedagogical theories. And so I want to say quite a bit more about that, about instruction maybe being misaligned with how students learn, where that comes from, and some of the things that we might see. Okay. All right. So generally, a lot of the ideas for teaching math, they are sort of influenced by constructivist approaches. And so what is constructivism if you're not sure? Well, at its most pure, it suggests that students should construct their own learning, things like invent their own algorithms, that sort of thing. It influences techniques like things called inquiry-based approaches or discovery-based approaches. You might hear things like 21st century learning, etc. And I'm going to give some examples of what this ends up looking like on the next few slides. And there are a few other things that I think influence math instruction. People want conceptual understanding, and they want to develop problem solving, and they want to keep students engaged. They want students to like math, and like I want all those things too. Of course I do. You know, I want students to understand math. I want students to be able to problem solve, and I want them to like math. This is more important to a mathematician really than anybody, right? But the problem is the assumption that these outcomes are best achieved by, say, minimizing teacher instruction and practice. And there are just also like, I'm going to talk a bit about conceptual understanding because I think there's a lot of misconceptions about what that means. And frankly, I'm not even sure what it means anymore. So in the next few slides, I'm going to talk about why, this may be well-intentioned, but the approaches used often end up maybe undermining understanding, undermining problem solving, and undermining engagement. Okay, so I'm going to talk about what this may end up looking like, and this isn't always. It's just sort of some of the things that I've observed over time. So what this might look like, and this is a big slide, so I'll give you a second just to read it. So we might see like a lot of emphasis on things like project or group work or concrete materials like hands-on materials like base 10 blocks, um, pizzas, that sort of thing. And that sort of thing, it might be good to introduce a concept, but they're often used beyond the point where they're helpful, like even as computational tools. There's a preference for exposing students to multiple strategies rather than teaching efficient, say, standard algorithms explicitly. The idea might be that they could even invent their own algorithms or choose from a large pool of strategies. Then structured practice tends to be de-emphasized. It's sometimes referred to as rote, or it's assumed that it works against understanding. And instruction frequently follows a top-down approach. Start with problem solving, and the idea would be that the other skills, like those knowledge skills, those facts, those procedures would just follow. That understanding would emerge through exploration. And of course, technology is often relied on to support or replace fluency with those basic skills. And then the teacher's role is often reframed. The teacher is seen maybe as a guide on the side instead of a sage on the stage. And some of these things, they might sound fine, like it, and they might be fine, like if they're used judiciously, right? But the problem occurs when they end up being the default instructional techniques. And that goes especially for novice learners or students who struggle. So I'm going to give you an example, and I'll kind of go through this kind of quickly, but I'm going to give you an example of, and this is from a textbook, a very common, popular textbook used in Canada, but it's not unique to Canada. I've seen this in US textbooks, for example, and it shows you what I mean by sort of this multiple strategy idea that I think basic arithmetic has been turned into something extremely complicated. So here's the example. Okay, so the idea here is, you're going to teach the students how to multiply two-digit numbers. So let's do 21 by 13. Okay, so they're going to use three strategies. They're going to teach three strategies to find this product. Okay, so we start off with Rami. He's going to model the problem with base 10 blocks. These are base 10 blocks. So he draws an array, a rectangle. It's a 21 by 13 rectangle. And when he does that, he notices he has two hundreds and he has seven tens and he has three ones. And so then he adds them up, he gets 273. Okay. And this may look neat. It may be like great. It's a nice way to get a kid to understand multiplication, but like keep in mind, like these are novice learners. There is a lot going on here. And think about the cognitive work here before the student even gets to the arithmetic. But the problem is too that it doesn't stop there. So then the second approach. Okay, so here's another way you could do it. And Keisha's going to use grid paper. Rami did 21 rows and 13 columns, but Keisha is going to do 13 rows and 21 columns. And so she notices, she's got one 10 block in the column, and then she's got like 6 10 blocks in the rows, and she adds those up, and she's got 60. So that gives her 60. She's got 3 1 blocks. She adds them up, and she too gets 273. Okay. And then the third approach, and they're going to teach all of these. So now Samuel is going to do it without base 10 blocks and without grid paper, and he's going to essentially use the distributive law. He's using the distributive law like this, but it's not say that that's what that is. And students might be required to do all of these methods. The base 10 blocks they may be treated as computational tools. And if they do learn the standard vertical algorithm, it may be treated as just like another algorithm, no better than using base 10 blocks. And, this is all very time consuming, and it creates a lot of cognitive load for novice learners. And I think, a lot of this, and I talked about conceptual understanding, and I put it in quotes. And I think a lot of it has to do with, well, two things. I think one of the things is there's a misunderstanding about conceptual understanding. And then the other thing is, I don't think it's necessarily recognized that this creates cognitive overload so that students actually don't learn anything. So I wanted to talk a little bit about understanding. So I call this misunderstandings about understanding. So first of all, there's this false dichotomy between conceptual understanding and procedures. So let's let you look at this for a second. And I think that Hung Si Woo is part of this series on math education, and that's great. And he has this wonderful article on the false dichotomy between conceptual understanding and procedures. It's assumed that if you're going to teach procedures, that it comes at the expense of conceptual understanding. And of course, I get accused of this all the time, that because I want students to have basic skills, I want them to be able to do procedures fluently, people will accuse me of not caring about conceptual understanding, which I've always found kind of absurd because like I am a mathematician. It's kind of like what I do, like understanding is very important to us. But I think it's more than that false dichotomy. Like it's a problem with the phrase conceptual understanding itself. Like it is not well defined. Nobody really knows what it means. And when you don't know what it means, you can't measure it and you can't possibly know when students have it. And so it ends up being conflated with these hands-on activities, manipulatives, those are like the base 10 blocks, and pictures and multiple strategies and discovery learning. So for example, someone might think that in order for a student to have conceptual understanding, they must be able to demonstrate they can do something in 3 different ways, or that they must be able to demonstrate it using hands-on materials. And then if they're not getting that, the other thing is it's often assumed that they should have conceptual understanding before skill, and then it will take a whole awful lot of time to get that conceptual understanding when it's become this big, complicated thing that takes a long time. So I do want to mention, like, this assumption that understanding has to come before procedure just isn't right. Like, of course, understanding can absolutely come after skills. In fact, I have found, like when you practice something a lot and you do the procedures a lot, you start seeing the patterns. You start seeing why things work the way they do. The understanding piece can come much later than the skill, right? And I mean, it's interesting, like, because to me, understanding in math what it means is something like, well, do you know what a definition means, right? Can you apply a theorem? Would you be able to, do you know why a procedure works in the way it does? And I think it's the teacher's job to be able to explain that, to explain why things work. Like we should know that everything in math comes from somewhere, right? We don't just make this stuff up. Like we don't just blindly follow procedures. Like there's a reason for everything. But I think it's the teacher's job to explain that. I don't think that the kids necessarily have to continually regurgitate this stuff. And I think often it's quite difficult for them. And like I said, that understanding could come later. And I want to give this other example, and this is from a Norwegian article that was just published in December. So I'll let you take a look at it, and then I'm going to talk about some specific things from this article. So this is just a piece from the article, and I was interviewed for the article, so that was kind of fun. And I have a Norwegian last name, but it comes from my father-in-law who came to Canada from Norway, and we don't pronounce it in the Norwegian way anymore. Okay, so let's talk a bit about this. So in the article, he went to this classroom. It's a second grade primary school in Trondheim. And the question is, are 15 plus 3 and 3 plus 15 the same? And the students explore this over the next hour and a half using physical tasks. Like I said, that's quite common, either alone or in groups. And the teacher notes that a lot has happened since she herself was a student. And the main difference is that we learned algorithms and rules, but now students will discover it for themselves. And the alarming piece of this for me is the last line that in a 2019 survey of fourth grade math teachers, fewer than 3 in 10 said that they explain new math or tell students how to calculate in the vast majority of lessons. Okay, so like I said, this all is sort of that constructivist influence, right? And an hour and a half is an awful lot of time to spend on that one thing as well. Like I can certainly think of better ways to do this. So on that note, there is an opportunity cost here. Okay, so I'll give you a minute to think about what I've written here. So the opportunity cost. So first of all, like think about that last one, right? It was, the commutativity property of addition, right? Is 3 plus 15 equal to 15 plus 3. They spent an hour and a half exploring that, right? And what happens when you're doing these types of activities a lot for the simplest things, like students then they don't get enough practice, right? They don't get enough practice. They like time spent with all the drawing, the explaining, the multiple strategies, managing those complex representations. It's like time spent not practicing those core skills. And like the way you get good at math is practice. You need a lot of practice to get good at math. And, like secondly, like these overcomplicated methods, these multiple strategies, they cause cognitive overload. Students they're juggling the diagrams, the decompositions, the explanations, often before the underlying skills are even secure. And without clear, direct instruction or explicit instruction, many students, they just won't learn. Like there are students who can learn through discovery, right? There are students who will learn no matter what you do. Advanced students, for example, may just learn, right? But most students won't. Like most students need to be taught how to do things. They need a teacher to show them how to do things and get lots of support and practice. So, the result is really a lot of wasted instructional time, in my view, and lost learning opportunities. Like honestly, and again, I'm not saying this wasn't any fault to my teachers. It is the system that my kids' teachers, it's the system that they are working in and what they are advised to do, what they were taught to do. But like there were days when like it seemed like my kids didn't do any math at school. They weren't learning. And my husband and I are both mathematicians, and we taught them ourselves. And I don't really know how it would have gone for them if we hadn't. But these gaps, they compound. Like gaps in foundational skills, they don't stay small, as I talked about earlier. They accumulate year after year, and it makes learning math a lot harder, a lot slower, and a lot more frustrating. Okay, so some of that. Now, what about problem solving? So I talked about conceptual understanding, and I think some of the issues there. And well, what about problem solving? Because we want students to be able to solve problems. We do not just want students to be good at procedures. Like the whole point is you want them to be able to use those procedures to solve problems. Okay, well, it might seem like the best way to teach problem solving is by giving students complex problems. That's true, but only if they have the tools to solve those problems, right? So, like problem solving and critical thinking, these are not like generic skills that can be taught independently of content. Like problem solving in math is content dependent. So the way it works is you have foundational math knowledge. You can then use it. For one thing, it reduces cognitive load. Okay, so for instance, like say you want to solve a problem, and within that problem, you have to know 6 times 8. Okay. And say if you don't know that's 48, and you're spending a lot of time like coming up with your strategy to try to figure that out, it gets lost, right? And then you have trouble solving that problem, getting behind your peers. Okay. So there's the cognitive load aspect. But in addition, the foundational knowledge, it actually gives us the stuff to think with so that we can become effective problem solvers. It's about having stuff in your head. Like problem solving, it's not what we start with. It becomes possible after students have the knowledge and fluency to do it. So knowledge is kind of like the engine that we think with. And this isn't just me coming up with stuff because I've learned from my friends in educational psychology. There's this thing called the instructional hierarchy. So I'll give you a second just to look at it, and then I'm going to explain it really quickly. And you could think about it like this, like whenever you're learning or whenever someone's learning something new, they go through 4 stages. And it doesn't matter who you are or what you're learning. Like this applies to like my university students as much as it applies to a kid. It applies to someone learning to swim as much as it applies to someone learning how to do math. Okay? So um, you go through 4 stages when you're learning. And I always kind of use like the hockey analogy because I'm Canadian and people really get that here. But so you start like this. So the acquisition stage, in the acquisition stage, this is when you're first learning something. You're going to make a lot of errors. So with skating, for instance, the student is like up on the skates and they keep falling down and they're constantly falling down and they need an adult to show them how to stay up on the skates, just like a student needs a teacher to teach them how to do the math and give them a lot of support and a lot of explicit instruction and a lot of feedback. And then after a bit, the student starts being accurate, right? They're able to stay up on the skates. They're able to do the math problem, but they could be quite slow and they can't use it in new settings. And that's when you have to develop fluency, and that comes through a lot of practice. So in the fluency stage, a student may be accurate, but they're slow. And the goal is to get them to be able to do it faster with ease so that it becomes almost natural, automatic for them. So that's where you get lots of practice. So that's when the student's up on the skates, but they're very wobbly. You wouldn't want to put them in a hockey game because a hockey game isn't going to go that well, right? Okay, so now after that, when the student becomes fluent, so they're accurate and they're pretty quick, they can do things effortlessly, then you'll all know this because you teach math. You give them a problem that's outside of a setting that they've seen before and they have no idea what to do, right? So at that point, you want to like show them how to do things in different settings, right? Like vary the types of problems, etc. And after that, they're ready to go. They're ready for innovative problem solving. And like that top part, that's where you would apply. That would be a good place to bring in things like inquiry-based learning when the students have those skills. Okay, and then I just want to say a word about creativity. And like I had this really great guest on my podcast, and that episode just got released today. And he's a cognitive neuroscientist, and I asked him about creativity. And he said, well, what is creativity? And like, it basically means like you've got a lot of different pieces of knowledge and you can bring them together to create things. And that's what mathematical creativity is like, right? It's like, look, and I don't play chess. If you got me to play chess right now, I would not be able to do a good job, even if you kind of told me the rules, right? But experienced chess players, like they can see patterns, they can see moves, right? It's like when you know a lot of math and you've seen a lot of math and you've done a lot of math, you can kind of just sort of almost see in your mind like how something's gonna work. And you can pull these pieces of knowledge together to be creative. And so we can't skip those foundational skills. We need them if we want to be creative in math. And then the other thing I wanted to talk about is engagement, because that's the other thing I mentioned, that it's often, like, and it's fair. Like people want kids to like math. I want kids to like math. But how do you do that? Well, not by like getting rid of math, by like giving projects that have very little math in them, right? The way you get students to get engaged in math is by building math competency, because when you are competent in math, you like doing it, and then you do more math. And when you do more math, that builds math competency. Okay. And so like researchers are saying that the arrow points in the other direction. It's not engagement leads to math skills, it's math skills leads to engagement. So the way to get kids more engaged in math is to build math competency. And then the last thing I'm going to say about instruction, I'm going to say a word or two about explicit instruction, or sometimes called direct instruction with a little d and a little I. So explicit instruction, it matters. And I think you'll have Sarah Powell coming to Talking Your Series, and she knows a lot about the research on this. But I'll let you read this quote from Andreas Schleicher, I can't pronounce it, of the OECD. And he's saying that one of the most debated findings from PISA has been that teacher-directed instructional practices tend to better predict student achievement than student-oriented learning. And you saw that quote from the Norwegian article. I forgot already what the fraction was. 4 in 19 teachers surveyed said that they actually teach explicitly. And this has been a consistent finding in PISA. The pattern's clearly visible in both East and West, and that's correlational data, but experimental research finds the same thing. Showing students how to do things like using work examples, practice with feedback, it works better generally for than inquiry approaches. And I want to just sort of say that's for new learners, novice learners, and students who struggle. Inquiry works better at that. If you're going to use it, it works at that adaptation stage. And just to be clear, I should say, what we generally mean when we talk about explicit instruction, you could think of it as 5 things. So the first is that the teacher models for the students. They demonstrate concepts clearly and concisely. The second is that they break down concepts into manageable steps. So as an example, like those pictures I showed you about how to multiply 21 times 13, that would not be breaking things down into manageable steps. And it makes sense to break things down into manageable steps because it reduces cognitive load so that students are maybe will more easily learn that concept. Then fade support. So you gradually reduce the instructional guidance so that the students can gain independence because we want them to be independent, providing infrequent opportunities for students to respond and practice and giving feedback. And then the last one is practice, like creating good practice, purposeful practice, and opportunities for students to build mastery. Okay. Okay, so I've talked about all that. And then I wanted to talk a bit about, I want to highlight a couple countries. And, I highlight these ones because I think they're interesting. And the first one I want to talk about is England. And so these are TIMSS scores from England. And generally, if you ask me, I would say that TIMSS is a better test than PISA. I think TIMSS is better at seeing if students are going to be successful in later math. It tests more curricular content than PISA. But I find it interesting because England scores seem to be increasing, and you see the slight dip after COVID, which you would expect. That's on year 9, I guess, or year 5. But their scores seem to be increasing. Well, a lot of other countries decreased, and then they're punching pretty high, like they're up there almost with some of the East Asian countries. So I find this really interesting. And then the other thing I found interesting is just the difference between England and Scotland. And I find this especially interesting if you look at this. So Scotland is in red and England is in blue. And you do see the dip after COVID for sure. But you see Scotland going down and England going up before that. And you can look at the PISA rank. So in 2009, England was 27th on PISA and Scotland was 21. And then in 2022, England was 11 on PISA and Scotland was 30. So you might wonder, like, what happened there? But it's interesting because it was maybe kind of like a natural educational experiment. And I don't live in England, I don't live in Scotland, but I did go to the source. I had Nick Gibb on my podcast, who was the Minister of State for Schools in England, and I asked him, "What did you do?" And so it was kind of like a natural educational experiment. And England and Scotland took quite different approaches to education. So I'll tell you some of the things that he told me, and he has a book called Reforming Lessons, which I've also read. And so I'll tell you some of the things he told me about math. Okay, so one of the things he told me is that they focused on improving primary math, which is like for the same reasons that I think it's important to focus on improving primary math, because I think that's sort of the foundation for everything. And like I always say, math is hierarchical. And they looked at the Singapore curriculum. He went to Singapore, he went to Shanghai, he went to Hong Kong to observe what was happening there, and implemented a clear knowledge-based curriculum versus Scotland, which I understand has more of a competency-based curriculum. We have a curriculum here like that here in Canada, in British Columbia, and it's very vague. And they sent teachers to Shanghai, and Shanghai teachers came to England to observe teaching, right? So to see how they taught math in Shanghai. And there are some other things like I find particularly interesting that he established the Education Endowment Fund, which vets education research. And like you do have to be careful with education research because basically everything in education is called research-based, but there's really no standard for what research-based actually means. Like it doesn't mean like in medicine when someone says something's research-based, it usually means like there was randomized controlled trials and they were replicated and we can feel relatively good about it. With education, it could mean like an opinion piece even sometimes, like I've seen that. So and it makes it really hard for teachers to know what actually is research based versus what is not. Another good example is you'll hear that something's research based, but then when you look at the research, and I've done this, you'll see that they didn't actually measure if it improved math outcomes. Like I would think, like if you have a math program and you want it to know if it's working, like isn't that the thing you'd check? Like if it actually measured math outcomes, like if it actually improved math outcomes, but it might have measured something like engagement, which you can't even really measure, right? So I thought that was rather interesting. And this isn't everything, like there were quite a few other things he told me about, but these are a few of the things that stuck with me. And I'll actually give you a link to that podcast episode if you're interested. I found it really interesting. And then the other country I wanted to talk about was Portugal. And I hope my good friend Nuno Credo is listening. And I'm a huge fan. And I also had him on my podcast. And so he was actually a minister of education in Portugal. And you can see like this is rather remarkable. And this is I grabbed this right from the OECD. They always have France as the comparator. I don't know why. But so France is in blue and Portugal is in green. And you can see that Portugal improved their scores quite a bit over that one period, and then they decreased a lot. And Nuno, by the way, if you don't know him, he's a mathematician. And I think that's amazing. And, maybe all the math problems could be solved if the mathematicians would become the education ministers. But so I talked to Nuno too on my podcast, and he told me about some of the reforms that were made in Portugal. And so I'll let you take a look at that. So, like England, they implemented a knowledge-based curriculum with clear goals. He told me before that there was a lot of emphasis on things like projects or civics education and things like that. And Nuno will say everything starts with the curriculum, a good curriculum. It tells you what your goals are, it tells you where you want to go, and then you test. You test that the those goals have been met. And they provided extra help for failing students, and they increased the top students and reduced the low performers. So some similarities that with what happened in England, and talking to both of them, another thing was that they both really they educated themselves on, you know, evidence-based education, particularly the kind of stuff that is in line with what cognitive psychologists are saying, like about cognitive load and things like that. A good book to read on that would be E.D. Hirsch's book, The Schools We Need. I think that's what it's called, and Why We Don't Have Them. And another book by Dan Willingham that a lot of people, or Why Don't Students Like School? I think it's called, by Dan Willingham. So anyway, I really enjoyed talking to them and hearing about the reforms there. And you could take a look at or listen to those podcasts if you'd like. Here are the QR codes. And of course, you can find them just on my podcast page. It's on every podcast app and on YouTube. Okay, and so I'm going to summarize. And so I'm going to pull sort of the main points together that I talked about today. Again, math is hierarchical. When students miss key content and foundational skills, those gaps compound over time. Second, strong foundations really matter. They make problem solving possible. They make later math possible. Fluency reduces cognitive load, and it really, what it does, it frees attention for higher level thinking. And third, I think, we know some of the things that would improve outcomes, like clear and rigorous curricula, assessments aligned to those curricula, explicit instruction, especially for novice learners. And finally, we do have some international examples that show that when systems make these changes deliberately, that results improve at scale. And that's the end of my talk. So thank you very much, and I would be happy to take questions.
Thank you, Anna. Okay, right. Where to begin? No, that was fascinating. Thank you so much. Um, Definitely enjoying listening and watching along, as I'm sure everybody else was in the live stream. And I really like the use of examples in England and Scotland, obviously, as someone who
Really?
is
Okay.
based in the UK. Yeah, yeah, yeah,
I'm not
Okay,
an
so
expert.
no, no, no,
Yeah.
no. It was
Yeah.
fantastic. Um, Right, so we've got a few questions that have come in, which I will
Okay.
get to in just a moment. But just to reiterate and clarify for everyone watching the stream, we have now added the link to the Google form where you can submit questions. That is in the video description box. So just below where you are watching this on YouTube, there is a link there. I think you might have to copy and paste it because we've been having issues with YouTube. YouTube has not worked well for us today. But nonetheless, please do, if you have any questions, that is where they can be submitted. They will come up and then I will put some of those to Anna in the next sort of 15 minutes or so, I think is what we're hoping. Um, so I'm going to have a look at what questions we have already.
Okay.
So I think there's one that sort of seems to be a bit of a clarification possible question, which is coming from Josh. I think I'll start with that.
Okay.
So Josh has asked if you could possibly expand on the comment that problem solving is not an independent skill. It depends on content knowledge and where that came from.
Well, I think that you know, okay. So what I mean by that is in order to solve problems in your domain, you need to have knowledge in that domain. It doesn't mean you're going to be able to do that problem solving in a different domain, right? Like, okay, I can solve problems, say, in algebraic combinatorics, but I can't solve problems in functional analysis right now. Like maybe I could if I learned functional analysis better, right? But I don't have the tools to solve those problems. So I think it really is domain specific, right? You have to have the knowledge in that field to solve those problems.
Okay. Yeah. I mean, so to just to complete what Josh has mentioned in the question as well, he just said was under the impression that literature said problem solving is a skill that can be improved independently through practice and one that can transfer between disciplines and to new topics.
I don't
So
know if
I
it
suppose
can.
you're yeah.
That isn't exactly what I've heard people say, right?
Okay. Hmm.
I mean it's possible, like certain elements of problem solving say, but I don't think you can necessarily transfer problem solving skills from one domain into a completely different domain.
Hmm. Yeah, I do agree with you. I think that there is like a threshold amount of knowledge, isn't there? Like if you just don't have the knowledge, you yeah, yeah, okay. Um okay, thank you, Josh. Right, there's a load more questions coming in and I'm now feeling very overwhelmed, but thank you. Please
Oh
keep sending them.
no.
Okay, right, let's okay, this was a good one, and I think there's one or two here that are sort of touching on this theme. Um there's a very long, this is coming from Barry, who's a retired maths teacher. There's a lot of sort of long things, but I think the main point of the question is asking, what do you see as the most effective ways to support students in grades 9 to 12 who have kind of fallen behind on those basic skills? So I
Oh my
guess perhaps a
God.
little bit more like practical. Like, what do you
I
do if you've got some
know.
students in those more advanced bit and they're missing those foundational gaps that you mentioned in the lecture?
Yeah, you have to address the foundational gaps. Like it's so, by the way, and when I talk to teachers, this is kind of like the most common question I get asked because that is what's happening, right? So these gaps are compounding, and you have teachers in like high school, and they're dealing with kids who don't know their times tables, right? So actually, you have to address the foundational gaps. They've got to get like practice on those skills that they are missing, right? So sending stuff home with kids to give them extra practice. If you can get like them pulled out, like if there are resource teachers in your school that can help those kids address those gaps. So the first thing is to like look at the things you want to teach them, figure out what those things are they need to be able to do those problems and brush up on those skills. Like,
So I guess a
honestly,
follow-up
yeah,
a follow-up
yeah,
from me then is how would you identify those gaps if they're not, it's not as simple as I'm sort of imagining from my own experience, let's say at
yes,
university level,
yeah,
where if a student is struggling to begin on a problem, it's quite
yeah.
hard to know that it's because of a certain gap in their knowledge.
You have to give diagnostic tests. So you have to figure out like what are the skills that I'm going to need my students to know to solve these problems. You've got to give a diagnostic test and see what they are and see what they don't know, and then target those skills. I mean, the other thing
Mhm.
I do is like, I mean, I teach at a liberal arts university. We have students that come into calculus and they're missing a lot of skills. And so the other thing you can do is like, if you know that for that particular unit, okay, so say like, I'm teaching limits, right? And oftentimes students can't do limits because they can't factor polynomials. Well, then within that unit, before they do those limit problems, I give them a bunch of problems, getting them to practice factoring polynomials. So that's an analogy, right? But you can do things like that that would help at that moment get them prepped for that next skill. I mean, oftentimes the other thing is like the question is it that they never learned that skill, like they never mastered it, or is it that they've just forgotten? Because sometimes it's just that they've just forgotten and they just need to brush up on that, which means they just need some practice and maybe some additional instruction. Like you could give them like little mini videos and things like that too.
Mm. Okay, thank you. And I also I've just realized because I got overwhelmed by all the questions. I wrongly attributed that to Barry. That was from Paul. So sorry,
Okay.
Paul. Sorry,
Oh,
Paul and
oh
Barry, if you're still
dear.
watching.
Okay.
I would like to make sure the
Good
questions
question, Paul.
correctly attributed. Right. Okay, this is a fun one. So this is coming from Bhutan, the University of Kurdistan, who would like to know if you could just change one thing in how mathematics is taught worldwide, what would that be? I love a question like
Um,
this. I love a hypothetical.
yeah. Okay. One thing. I get to change
Hmm.
one thing. One thing. Um, honestly, I think it would be and like this I had to be careful how I say this and but if it was only one thing, I would
Yeah.
and I would pick to have math specialist teachers who have like really strong math backgrounds in elementary school. That's what I would pick.
Hmm.
That would be my thing. Because I think that, I mean, I think it would be easier for them to push back against some of the stuff that just is not making a lot of sense, like teaching, through starting with problems and that sort of thing. Because I think, when you have a strong math background, that you've got to build up. That would be the one thing. But, I don't think that's necessary. I think that we can change a lot of things and make math education better. I sort
Hmm.
of don't really like the one thing questions.
It's always tricky. That's why it's fun though, isn't
I
it?
know, but curriculum
It's
would
very
be big too.
hypothetical. We are
Curriculum would be
aware it is
big.
extremely, yeah.
Like I'm kind of, with Nuno Credo, he says if you have a good curriculum and good testing, everything else will follow. And that may be true, you know?
Mm. Um, okay, right. So to go back to the gaps in knowledge topic that we were just discussing. So this is a question that's come in from Jonathan, who has asked, with math being so hierarchical, where do we draw the line in the amount of information a student doesn't know and needing to hold a student back? For example, if fraction proficiency is directly correlated to success in algebra, if a student cannot complete operations with fractions, do we hold them back until they can?
You mean like hold them back, like not let them progress to the next grade? Is
I
that what he
think that is the
means?
way I am interpreting the question. It's saying, like, I guess, is there a place for that? Should we be using that, not using that? Just your thoughts on
Well, we
that
would
idea, I
never
guess.
do something like that in Canada. Okay. So this is like, it's just like not acceptable, right? So, no, I think that the goal has to be to fix these gaps along the way. Identify the gaps, fix the gaps. Like I think it should be possible to fix those gaps, right? The only issue is with what he's asking. Like it's almost sometimes impossible to be able to solve a math problem or work with the math you're being taught or even understand what's going on if you don't know those prerequisite skills. Like, I think it makes sense to do things like flexible ability grouping. In other words, students work with students who may also have those difficulties. They get the targeted support, and hopefully we can then get them up into the next level, right? But I mean, I think
Mm.
streaming is a good idea after a certain point. I think that's a good idea. I don't know about holding students back a grade. Maybe, if it's quite bad, that probably does make sense, depending on how big those gaps are. Like,
Mm.
definitely the issue of having all students in the same class and like grade 8 to 12 when there are these huge gaps it does seem to be an issue, right? That's where streaming kind of comes into it. Or what do you call it there? Tracking? Or
I would call them sets. Like I remember
oh yeah,
being, there was
setting.
like,
Right. Sorry, I knew that.
yeah,
Okay,
like
I
set
did
one,
know
set
that.
two, set
Setting.
three, etc.
Yeah,
Yeah.
okay. So do you set at what grade would you set in England?
Okay, I can only go off my own personal experience, which was when I was 11. So would that so I it would call it year seven in the UK. Maybe is that grade
Ah,
eight in the US
okay.
possibly?
Mm-hmm. Okay. Yeah, like that makes sense.
Yeah, sort of that's the point in the UK system where you split up from primary
Yeah.
school when you do everything to having specific teachers for specific subjects. Then you begin
Yes,
to, yes, sort
that
of
makes sense.
stream or set the students. Yeah.
Yeah. And then before that, you do kind of have to figure out which students are having difficulty with those skills and maybe think of doing flexible ability grouping within the classes to target those skills, get them up to speed, and hopefully move them.
So this is an interesting question that's just come in from Kelly, which mentions, for example, in judo, that's all
Yeah.
sports, you
Yeah,
would
my
teach
sister has a
kids the
black
sw
belt in judo.
Oh, well, there we go.
Yeah.
Right, perfect.
Yeah.
It says, so Kelly has said you would teach the smallest kids with the best teachers. So could we put very qualified people in the younger years? Therefore, like, is that a way of thinking about it?
Yeah, for sure we could. Definitely.
Hmm.
What's stopping us, right?
I guess from my own perhaps personal perspective, like if you were a very high level qualified mathematician, would you necessarily want to teach
Yeah,
the
I
younger
know.
students?
I mean, I
I
personally
suppose,
like
but
I like working with younger students. Like as I told you, I have a an after school program for grades 4, 5, and 6. I mean, what I like about younger students is they actually get really excited about math, whereas somehow over the years, I mean, you teach at Oxford. I guess you probably don't see this, but we have students that are forced to take math and they often don't really want to be there. And so you go to a lot of work to get them excited about being there and that sort of thing. But with young kids, it's like this clean slate. Like they actually love math you know? So, but you are correct. That might be true that people with high level math knowledge maybe don't want to go into elementary school. Pay more.
mm.
That would do it,
That
right?
that was the second part of Kelly's question. Yeah,
Yeah,
was it? It was actually saying, should we just pay them more to get them to do that?
yeah,
Um,
yeah.
okay. Another one here from Jan, who's a school leader, who has asked, is there hope that we can see these ideas about evidence-informed teaching and knowledge-rich curriculum spread into education departments, or is there still very strong opposition there? So you kind of
That would
hinted a
be the,
lot that
oh
you've
yeah, I
spoken to
did hint a
people
lot
in this
about that.
policy area, which I think is always
Hmm.
interesting to
Yep,
hear about. Do they listen?
I did hint a lot about that. And I think there are some positive developments in this area. Okay. Well, okay. So, like Sweden, for instance, it's going to be, and again, I get my information from other people. So I had this wonderful education professor from Sweden called Jonas Linderoth on my podcast not too long ago. And he told me that in Sweden, they're going to be required to teach cognitive load and cognitive science principles in their education classes. So they're going to be required to do that. So I'd say that's very positive. I see a lot of positive developments coming out of Australia. Um, you know, hopefully we can get something going in other parts of the world too. But yeah, that would be great. Like it would be great if teachers were taught about these things when they're in their teacher prep programs.
Hmm. And I think a very nice final question to end on as we come up towards the sort of 15, 20 minutes that we were hoping to do for Q&A. So this is to go back. It's another question again from Bhutan who asked the first one about the tricky one about one thing, but then the second part of the question,
Oh, I don't want
what
any more of this.
separates? No, no,
Okay.
no, no, no. This is a good one to end on, I think.
Okay. Yeah, I
Um,
know, I'm just joking.
what separates a good maths teacher from an exceptional one?
Okay. Um, yeah, a good math teacher from an exceptional one. Okay, so what would an exceptional math teacher look like? Okay, so an exceptional math teacher, first of all, they know the math, right? They know
Hmm.
the math that follows it because then they know what they're preparing students for. And by the way, like when I say these things, this doesn't mean you can't be a good math teacher if you're not in that position, right? I mean, I think good resources, good textbooks can really help people and if they maybe don't have a strong math background. Okay. So they know the math, right? They're passionate about the math. Like being passionate is like it is a really important thing. It rubs off onto students. It makes them excited about the math. Like we all want people who are teaching us who seem to actually like what they're teaching, right? They have some knowledge of how to teach well, right? So they know to break things down into component parts. They know to like scaffold instruction. They know how to model, give lots of feedback. There's a lot of interaction in their classes between them and the students. It's not just them like at the front of the room talking. There's a lot of interaction and checking for understanding. They're making sure their students learned regularly. And there was something else I wanted to mention, but I forgot what it was. Um, shoot. Okay. Those are kind of the main things I'd say. The other
And
thing will
I,
come
I
to
will
me.
just, yeah, and I will just second the passion. I think that as sort of, I guess a
Oh,
slightly
I know what it
different.
was.
Oh, go on.
Tom, I know what it was. They care about struggling students, they care about students who do fine, and they care about advanced students. Because a lot of times I think the advanced students don't get support either, right? So the struggling students are falling behind, and they need a lot of support, but advanced students also deserve extra challenge. And so I think that's important as well. That's it.
Perfect. Well, thank you very much,
Well, thank
Anna,
you.
and thank you to everyone for joining. Thank you to everyone for sending your questions in. I can see there are many more questions. Sorry, I couldn't get to them all.
They
Um,
could email me as
there we go.
well. And, I'll get back to you. It might be a few days, but I'll get back. So happy to answer more questions.
Amazing. And this will, of course, the entire lecture and this Q&A section will, of course, be available on YouTube indefinitely, having trimmed the awkward silences at the beginning. And we will be back in 4 or 5 weeks. I'm just going to quickly cheat and look at my calendar. On the 13th of February, we'll be back for lecture 2 in the series. So again, thank you everyone for joining. Thank you once again, Anna. That
Thank you
was
so
that was
much.
fantastic. Learned a
Thank
lot,
you.
as I'm sure everyone else did. And do join us again in 4 or 5 weeks' time.